background of the quantum computers. I don't have enough time to go over it, but technically we have different machines. IBM has the NISQ computers, near intermediate scale quantum computers, which is the similar processors to classical computers, but they cool it down to minus 273, absolute zero, to make it superconducting. And there are other technologies like nuclear, ion-based, and others that is used in quantum computers. Now, one of the issue over the superconducting material is the noisy environment in those, because they are shooting electrons or waves into the processor, and rotation, calculating their rotation, and the base operation of the quantum computers should be done in the scale of atoms, and that could become problematic when you wanted to measure it. So the error occurrence probability is one of the research areas in this quantum computers, especially NISQ. And this paper is proposing a new method to solve this problem. So this is the background that I was talking about. The qubits formation can be defined in mathematical equation in linear algebra by having the alpha times 0 state, or cat0, plus beta cat1. And you can decompose this into the dot product of the alpha beta with the each states. And the probability states the alpha and beta to the power of 2 is 1 or 100%. There are many operations in quantum, but it depends on the back end or the hardware, which if they can be support that or not. Technically, in theory, we have H, Z, C naught gate or CX, unitary gates, U3, etc., and like many more. Like we have phase estimation, we have T rotation. These are like a basic gate operation. If you wanted to compare it to the classical computing, it would be adding, multiplication, and other operation that we do. The gates that we all studied in operating system. We can have multiple circuits for each quantum algorithm. What that means is that, as you can see in this picture, we can define one quantum computer based on supported gates or qubits, number of the qubits that we are using in each quantum computer, and we can set up these differently. Like the same circuit can be mapped differently on each backend. So this paper talks about the qubit CNOT gate, two-gate error being mapped on different ways on different hardware IBM Qs, and they use the heuristical collected data to study the stochastic components and the different statistical features of each quantum computer, especially T1, T2 errors. Oh, I have to explain what is T1 and T2. The T1 is the amount of time that you have for each electron or qubit before it decays into the state 0. So if you put it in state 1, you probably get 88% or 90% of that electron or qubit to be close to 1. And then the time that you have before normally this wave or electron decays into the state 0, that would be T1 error. And the T2 is other qubits causing your specific qubit, let's say qubit 0, to rotate or change a state from 0 or 1 to some other state. So the authors of this paper study these features, and they wanted to, this is just representation of the qubit, C0 qubit correlation between 0 and 1, 1 and 2, and how much systematic error that you get, or how much stochastic error the component that each one have. Systematic is the correlation between, I'm going to show it later, between the qubits, and stochastic variation is how much, because you run your experiment like let's say 1,000 times, how much difference each thousand you get from expected result. Oh, actually, I have the definition over here. For instance, qubit 0 for systematic can be vary in different qubits. Qubit 0 and 3 are higher average readout errors compared to qubit 4. Let's say that they at the beginning they observe these issues. So these systematic errors and stochastic can be used later on in for creating a system that I'm going to go over. Before that, let's move over some terms and definition. I'm going to move fast over this area because time is limited. Gate operation error is talk about when you wanted to put your qubit in some rotation, how much error you get from that. Let's say that I want to put my qubit at absolutely between 0 and 1 half, but because of the errors, I get somewhere between that with some extra epsilon error. Readout is when you wanted to read the qubit and you get errors. And quantum algorithm is whatever application that you have. This is not related to errors. This is just a definition. Circuit mapping is a blueprint of quantum algorithm into the hardware. So in your quantum algorithm, you can have qubits, you can have even abstract method that I wanted to run some machine learning in quantum on quantum computers. Perfect. And then you need to map it. That is done by a compiler and circuit mapping. Replication and trials is when you oh, I need to admit. Replication and trials is how many times you wanted to run that circuit map on a quantum hardware. There are two levels of quantum benchmarking method. One of them is replication and trials. You repeat your experiment many times, and then you combine the result, and then you come up with like a number, the summation of all of those trials that you've done, or you add. There's like a shots or replicas provided by IBM or other companies inside the quantum CPU to having multiple runs in internally. Excuse me. So from this two type, we have observed output and correct output. The observed output is the probability of each output state and provided result that you get. The correct one is the one that is based on theory or the computation in simulators without errors or anything like that. Normally, what people do is to run partial quantum algorithm or circuit on simulator and then calculate the result and then run the exact one on quantum computer and then try to fix it. But as you can imagine, this is only applicable for 5 or 50 qubits, because if you wanted to simulate more than that, you're going to need a exabyte or even more than that of memory, and you need millions of CPU to simulate just one small algorithm, because that's a benefit of the quantum computer. They're fast, they are capable of solving NP problems faster, and the data that they can process it compared to the classical computers is going to blow up massively if you want to simulate that. So this paper talks about not using the simulator. I'm going to skip the unnecessary part because this is a long presentation. And how many people just left? Are we having trouble? Anyhow. This is a system design that they come up with. You have some gate readouts, heuristical data from the IBM machines, like T1 errors, T2, frequency of operation, readout errors, and other, etc. And you get the estimated circuit mapping on that machine, the best case scenario that you can run your quantum algorithm on the machine. And you feed that through, you choose your quantum circuit from A to Z to run it. And you calculate how much shift that you need to do over the systematic error. Systematic was based on T1, T2, and frequency errors. And then after that, you run the filter noise state, which is corrects the other errors that you get, the extra values, stochastic errors. And then finally, you get your final perfect estimation close to simulators, like even better. This is what they claimed. I didn't confirm their result, but they published in Supercomputing, which is not a bad conference. It's a high-tier conference. So I trust the author's word for it, but their system is not involved of any simulation. Normally, simulation is happening over this phase, the machine 1 to n. When you wanted to run some circuit, you simulate it on a simulator first and then see what the correct output is, and then calculate how much shift you need to do. And they done some other works by calculating the correlation between the gates and C0 between the qubits, which was useful for their assumption, but it's not sophisticated enough. They just ran some distance estimation for that part. I'm not going to go over the details because this is more related to my research, not for like general the audience to just bother themselves with these the stuff. But essentially what they achieved is this is this phase that you see, that selected maps with the correlated errors, they are being corrected, pushed down to the ideal situation. The star is ideal situation, and they're being pushed up or pushed down after calculation and getting corrected. And they run a couple of quantum algorithms on different machines on IBM Q. One of the famous algorithms in quantum is Bernstein-Verzani algorithm, and the other one that they was calculating, I don't have it over here. They ran other algorithm too, and they calculated the result, and they evaluated their approach, and they said, okay, this is good. And this is post experiment. When you wanted to solve the issue, you take the expected value of the how much error you get, you add it to your result you're reading from the qubits. But skip, because this is like too dense. So this is this is the algorithm that they run. 2 qubits BV algorithm or Bernstein-Verzani algorithm for up to 4 qubit, and they ran the quantum phase estimation, Simon's algorithm, and the circuit to stress X gate errors, which is like a basic dummy experiment with 1 H and X gate at the beginning, and then 8 H, which is rotation to the half. gates after that to just evaluate the performance of the quantum machine. So how much time do I have, Dr. Pham? Should I talk about the evaluation metrics too, or just go to the conclusion?
You can continue with your presentation. Do you guess how long you finish?
Okay, let me just mention it. There are two metrics to judge the efficiency of the paper that the authors just proposed. One was based on output estimation of the known algorithm, like for example, BV algorithm, you know what you should get at the end. And the other one was to calculate how much distance you get based on the error variance interval, which is your estimated value, and then you calculate the distance, and then you see how accurate your algorithm is. They use these two metrics, but this is not effective. One of the shortage of the paper was this is not effective for chemistry or machine learning application because the outcome of the algorithm is unknown to the user. So when you wanted to execute your machine or chemistry application on quantum machine or even a classical computer, when you wanted to create a neural network right now, unless you spend like many hours and then calculate every matrix by hand, you wouldn't know what's going to happen between. So, but you observe the learning rate and then you adjust your network based on that. Same thing for quantum computers. You don't know what the outcome. So this method is perfect for known quantum algorithm, but it might be need to be adjusted or changed for chemistry or machine learning algorithm. This is the final evaluation they went through for the entire system. From A to H, they showed parts implementation of their algorithm, and then using the systematic error correction plus a noise state estimation that they proposed, and then moved on onto the last one that shows like the perfect situation. But as I said, this is like when you know your result is going to be this 4. If you don't know it, you might boost up some other result and then get, for example, look at this one. This one on Melbourne machine, because it's super noisy, for outcome of 0011, you boost it because you know the result should be that. But if I just pick up the highest one, which is 0010, I'm boosting the wrong result. But for the other known algorithm, as I said, is working fine. So that's it. They have a couple of other observations similar to this one, but that one is the best one. There are more related works, like other related works to this one, but most likely the other people before these guys, they were using like dense matrix simulators in quantum computers or other techniques to come up with to fix the errors or come up with the shortage of this NISC. And that's it. Questions? Kyle, go ahead. Should I?